When we know how to find minimum of a function, we can use it for many practical purposes. One of them is least squares method, in short LSM, or least squares fit. This is a method how to fit a curve through points which may be obtained by some computation or as experimental data from some real-life experiment. So consider that we measure two variables, say x and y, and we measure a few pairs of these points, and if we visualize them, we get points like that. Sometimes this may be a result of some dependence of some function, of some deterministic law, which is simple, say linear, and these deviations, these differences, are just results of some noise, of some error, some measurement errors. That means we have a value where xi, well, we have a table of the xi and yi values, say 0, 0, 1, 2, some numbers, say 3, 1. And we want to find a line with some equations, say y is ax plus b. And we want the line to go close to the points. In a typical case, the points are not aligned, not exactly on one single line. There are something a little up and sometimes a little down. And we want to find the best line approximating these points. One way is to consider the distance of this point from the line in the vertical direction. And we want these deviations to be small. Well, if we make one of them to be small, say 0, we shift the line, then the others may increase. So we want to summarize all the deviations. For one single x, the point on the line is ax plus b. If this is for some particular measurement point xi, then the value on the line is axi plus b. And this point is the measured value, y sub I. So this difference tells us about this segment. And we want this to be small, but positive deviation and negative deviation, both are bad. So we take, if we sum just this, then large positive and large negative may give 0, which looks good, but it is not. So instead of summing the differences alone, we sum the squares. Second power square. This is where the name square comes from. Well, and then we consider the square of this distance and this distance and this distance and this one, this one, this one, this one, this one, all of them, and we sum. We take the sum. We consider sum for I running from 1 to capital N, which is the number of points. And this is a function, let's call it capital S, a sum, of these two parameters, of these two variables, A and B. And we want this function of two variables to be small. We want to find the minimum. It looks quite reasonable that some minimum may occur, because some squares will be never negative, only rarely 0, but it will be most probably positive. If you go far away from the points, if you take some strange A or strange B, then the differences will be large, and as may be large as you wish, But if the line goes close to these points, well, it looks like that some minimum may occur. We will come to this question later if the minimum is unique and so on. So first we have a function of two variables a and b, and we want to find the minimum. So we compute the partial derivatives. Let's start with partial derivative of f with respect to b. Derivative of sum is sum of derivatives. And derivative of square is 2 times the bracket. A xi plus b minus yi. Possibly times the derivative of the inner function, but the derivative of the bracket with respect to b is 1. And then we consider the derivative of s with respect to a, which is sum for I running from 1 to n. Again, 2 times the bracket. But once again, times the derivative of the inner function. And the derivative of the bracket itself with respect to a is xi. Well, and to find the minimum, we want these two derivatives to be equal to 0. Well, and this is a system of two equations for two unknowns a and b. And if we solve this, we have the stationary point, and it turns out this is the minimum, and we have the line. That's all. Well, let me simplify a little these two equations so that we get a form which is very easy to remember. First, we can divide by 2, and then we can sum these terms, and these terms, and then we can move the terms without the unknowns, a and b, we can move them to the right. So here we have sum of axi, but in this sum we can factor out a. And we have a, sum of xi, plus n times summing b is nb, and we move sum of y to the right by adding this expression. So we have sum of y on the right. Each sum means sum for I running from 1 to capital N. And here we can again divide by 2. When we expand this multiplication, we have axi squared. In this sum, we can factor out a, and we have a sum of xi squared. Then b is now multiplied by xi, so we have sum of bxi. We can factor out b, and we have sum of xi. And this term, multiplied by x, does not contain the unknowns a and b, so we can move it to the right by adding the sum. And we have sum of xi times yi. Again, I running from 1 to capital N. Well, and now when we divide by n, then we can write it this way: 1 over capital N, and disappears, 1 over capital N, 1 over capital N, 1 over capital N, and 1 over capital N. And we are only one step away from a very nice, very easy form of this system of equations. Look at this expression. We have some numbers, x1, x2, x3, up to xn. We sum all of them, and we divide by the number of terms. This is quite a well-known operation. called arithmetic mean or average. Let's denote this by x bar. Well, quite an easy operation. Similarly, here, if we have some values y1, y2, y3 up to y sub capital M, we add all these numbers and we divide by the number of them, we get the average or mean of these y values. Let's denote this y bar. We have also x average here. What about here? We take the numbers x1, x2, x3, we compute the second power, the square of them, and then we add and divide. So this is an average of the squares of the values. Let's call it x squared bar. First we take the numbers and we compute the second power, and then we average these squares. This is not the square of the average. Well, and finally, we have this expression when we take the pairs x1, y1, x2, y3, y2, x3, y3, and so on. We multiply, and then we average. And we can denote this as xy bar. This is just one single symbol, a shorthand, an abbreviation for 1 over capital N, sum of xi times yi. And using this notation, this system of equations can be written as ax bar plus b is y bar and ax squared bar plus bx bar is xy bar. Well, and I claim this to be very easy to remember. If we look at the first equation, ax bar plus b is y bar, it resembles the form of the line that we want to fit through the experimental points. Well, the letters has different meanings, right? This x and this y are some variables. Independent variable and dependent variable in the equation of the straight line. Here we have x bar, which is no more a variable. If x1, x2, x3 are some experimental results that were measured yesterday, the lab is closed today, the experimental setup is destroyed, but we have the experimental results, we have the data. Now x1, x2, x3 are constants today. So x bar is a constant, not a variable. X is a variable, x bar is a constant. So the meaning of the letters is quite different. But graphically, if you remember, if you are able to remember y is ax plus b, then you have no problems to remember ax bar plus b is y bar. Well, and the second equation is similar to this one, just one more x here, one more x here, one more x here. We know where this one more x comes from. It comes from here. When we differentiate it with respect to a, we have to multiply by the derivative of the inner function here by a. When we differentiate with respect to a, we must multiply by xi. Okay, so this is the system of two equations that we can use for the least squares method. Let me illustrate this for this system. So first we add the x values. 0 plus 1 plus 3 is 4. We add the y value 0 plus 2 plus 3 plus 1 is 3. We also prepare the product. 0 times 0 is 0, 1 times 2 is 2, 3 times 1 is 3, and we add 2 comes to 5. And we prepare squares of x, xi square. 0 square is 0, 1 square is 1, 3 square is 9. When we add, we have 10. And then we can, now if we divide these 4 sums by capital N, we get the averages. But we use this form just to remember the form of the system of equations, and we don't divide by n. So instead of x bar, we use sum of x. That means we go before this division by n. So a multiplied by 4. Then when we go before division of n, we must have ne, but we have 1, 2, 3 points, so n is 3. And instead of y bar, we use sum of y, which is 3. And the second equation, we use x square sum, which is 10, so 10a, plus b sum of x, that means 4b. And finally, xy sum is 5. Yeah, so we have this system of 2 equations. We can use Cramer's rule. The determinant of the system is 4, 3, 10, 4, which is 16 minus 30, which is minus 14. D1 is the determinant when we replace the first column with the right hand side column, 3, 5, 3, 4, which is 12 minus 15, which is minus 3, and finally E2 is the determinant of the matrix when we replace the second column with the right hand side column, 4, 10, 3, 5, which is 20, minus 30, which is minus 10. So the result is A is D1 divided by D, which is minus 3 divided by minus 14, which is 3 divided by 14, and B is D2 divided by D, which is minus 10 divided by minus 14, which is 5/7. Well, so the equation of the line is y is a, which is 3/14, x plus 5/7. Well, and we can plot these points along with the line. 0, 0 is here. 1, 2 is here. And 3, 1 is here. Well, I must say these points do not look like very much to lie along a straight line. And the equation, well, yeah, this coefficient is very small, close to 0, and this is some small number, well, yeah, something like that. Well, yeah, it was not very clever. This choice of points was not very clever. Okay, let me repeat this once again. So if we have a table of points, we can plot them in a plot, and we can consider a straight line going through these points, or close to these points. The practical computation looks like that. We have this system of equations where x bar, x square bar, y bar, and xy bar are the average values of x, or y, or x squared, or x times y. So we prepare these two columns in the table. We sum all the entries in individual columns, and we use these numbers to build this system of equations. We solve the system, say by Cramer's rule, and we have the parameters a, b, and then we have the equation of the line, which is the best fit through these experimental points.